Okay, so we ran out of some time today, but I'm going to discuss with you the Beer-Lambert law and the calibration curve method, which is the method we'll be using to find the concentration of our unknown phosphate solutions. So, first, the Beer-Lambert law takes the form A equals E, B, C. Now, an important note I want to pull out is that depending on different textbooks, B will sometimes equal L. They're the same thing. They're both the path length. So A is our absorbance. E is a constant at our given wavelength, or lambda. B, or L, is the path length, which is the width of the cuvette for our experiment. And most UV vis spectrometers, that was 1 centimeter. And C is the concentration. And we can see that it kind of mimics this form of the line of best fit of Y equals mx plus d. So, as we can see, our absorbance is Y, which makes sense because absorbance is our dependent value. It's the thing that depends on the thing we're changing, the independent value, which is X. So there's a little typo on this slide here. It says MC, in this case C for concentration, but it should be X, mx plus B. Which means M, or our slope of our line, is E times B. And then our intercept should be 0. Now, in our calibration curves, it will most likely not be 0 due to error. So what this means is we get a linear relationship between concentration and absorbance. And when we see, and once we do that with our standard samples, which are our known concentrations, we are then able to, when we have the absorbance of our unknown solution, we can find out where it is on the graph and find out the concentration of that unknown solution. So we'll go ahead and give an example of that. So what we'll use is Microsoft Excel. And we'll go ahead and plot our concentration. So I'm going to do this as if I was doing a different experiment, where I am doing a calibration curve of the concentration of lead. So to put that, I'm doing the concentration of lead, brackets in the concentration of, and I've recorded the absorbance. So I made standards at 0.5 molars, 1.5 molar, 2.5 molar, 3.5 molar, 4.5 molar, and 5.5 molar. And the absorbance values I got for those are 0.0376, 0.09, 6 and 1503. Three. 1.317. Once I have this data, I'm going to want to make my calibration curve graph. So I will insert scatter plot. It might automatically select the correct data. It might not. It did in this case. If it doesn't, or if it just puts a blank screen, what you'll do is you'll right click on my graph, click select data. You'll remove anything in this box by hitting the minus and add a new blank one. For the X values, you'll select your concentration. For your Y value, it'll try to automatically select things which might give you problems, so you'll clear that out. And select your corresponding absorbance values. And we can type our name in here. Absorbance versus concentration of lead. I'll use the brackets again. Molars, absorbance is unitless. I'll hit OK. And I have a properly typed graph. We'll want to add our chart elements. We'll want to axis titles. Remember, on our x-axis, we have concentration, lead, and molarity. And on our y-axis, we have absorbance. And we'll need to create all in the best fit, so we'll right-click on the data point, and a trend line. Make sure that is a linear trend line since we're doing linear analysis. And for analysis, you'll want the equation and the R-squared value. The R-squared value tells you how linear the line is, how well it fits the data. The closer it is to 1, the better it is. Bigger. There's just so we can see it better. So this is what we get. And we see it's very close to 1, so this is a very good calibration curve. So then, I use my standards, I create my calibration curve, because we use our standard solution like calibration curve. But then I have my unknown solutions. I have unknown 1, 2, and 3. And I put those in my spectrometer, and I got their values. I got an absorbance of 0.2678 for unknown 1, 0.1256 for 2, for 3, 0.426. So just by looking, you can see like unknown 1 is between, so if unknown is a 0.26, it'll be just between 0.25 and 0.3. So if we can see, it'll be around here between 4 and 5 molars. And we'll use our alignment as fit to find the exact value. Here. Here. So just as a reminder, our line of best fit was y equals 0.0556x plus 0.0093. We'll start with unknown 1, which had an absorbance of 0.2678. Remember, absorbance is our y, so we'll plug in y for absorbance. And solve for x, which is concentration. So subtract by 0.093 on both sides. Give me 0.258 equals 0.0556x. And to get x by itself, by 0.0556 on both sides. This gets me 4.65. And my units concentration on my graph were in molars. So we can do that again for unknown 2. Which had an absorbance of 0.1256. So we can plug that in for y on our line of best fit again. Again, we'll subtract both sides by 0.093. X will get me 2.9 molars. Then we have one more unknown, unknown 3, which had an absorbance of 0.0426. So again, we plug it into our line of best fit. So I encourage you to pause the video and try to find the concentration of unknown 3. Okay, and now that you've tried it, we will now solve for x. 6 is equal to 0.599 moles. So that is how we can use a calibration curve of our known standard solutions to find our unknown concentrations. So just to review, we performed a serial dilution. So that's where we took from our stock solution only one time. And we pipetted it out of there and transferred it into our volumetric flask. The amount that we needed and filled it up to line water. And for our second standard, we took from the flask beforehand, filled it with the needed amount, and then filled it this way with water. And we did that 6 times. And that's so we can dilute our stock solution to get a bunch of standard solutions or solutions in concentrations. Our calibration curve was our graph. We plotted absorbance versus concentration. And that allowed us to generate a line of best fit that we can then use to find for unknown solutions using their absorbance. There is a difference between extrapolation and interpolation. What we want to focus on is called interpolation, which is within the data. So on our line of best fit, if we have solution 1 or standard 1 here, sorry, standard 6 here, we want our unknowns to fall in between there and be on the curve. That is called interpolation. That is more accurate than extrapolation, which is where we have standard 1, standard 6. And then let's say our unknown is way after. If we're assuming this line remains linear all the way at higher concentrations, we're making a big assumption there. That's called extrapolation because it's not within the data. Absorption and transmittance. We talked about this last week. Absorption is the amount of light a sample absorbs, and transmission is the light that does not get absorbed, so it goes through. And this is what our spectrometer reads. It's the light that is transmitted. The photons that go through then hit the detector. Our blank sample is a sample that contains everything that we used in our sample and our standards minus the analyte. And this serves to remove anything in our solution, especially in the solvent or ABM, that might cause absorption of light that is not caused by phosphate. So this will minimize absorption. We won't calculate absorption that is caused not by organic. Our standard sample is our samples of our known concentration. And our unknown samples is what we don't know the concentration of. That's what we are solving for. Good luck on your lab report. Please look through your feedback on the last lab report. And I will see you next week.